Hello, welcome to our class, Heterogeneous Computing. Today, I'm going to talk about OpenCL examples. This is the first of the 3 sessions that we will use OpenCL examples to show you how to solve the problems using OpenCL programming. In today's lecture, we're going to look at 3 examples: matrix multiplication, image rotation, and image convolution. And for each of these 3 examples, we'll show you through demonstrations how the OpenCL program is designed, compiled, and executed. Matrix multiplication is a very classical parallel computing example that have been used in many different occasions. Here we have 2 input matrices, A and B. For each of these 2 matrices, it has a certain number of rows and a certain number of columns. For matrix A, we have a number of rows which we denote as height of A, HA. For the number of columns, we denote with WA, or width of A. Similarly, we denote the number of rows for B is HB, and number of columns for B is WB, as we show in this diagram here. There's a requirement here, which is the number of columns of A has to be equal the number of rows of B. This is because we have the matrix multiplication defined as each of these resulting elements in the matrix C. This element is actually the dot product of this row vector of A with this column vector of B. And we'll show you the exact calculation in the next slide. If we're implementing this matrix multiplication using a C program, and this is what we're going to have to write. We're essentially going to have nested loops so that we're going to go over each of these elements in the matrix C. And for each of this element in C, we're going to calculate the dot product of this row vector from A and this column vector from B. To implement this operation, we essentially have these 2 levels of loops. In the first loop, we're going to use iteration variable I to go through from 0 to height of A. This essentially is we're going to go over every single row of this matrix C. The second loop with variable J, and we're going to go through from 0 to the width of B. Essentially, we're going to go over every column in this matrix C. So at this point, we're going to calculate this single element of C with coordinates I and J. And to do that, we're actually doing the dot product of these 2 vectors. So in the third loop, where we have the variable K iterates from 0 to the width of A. So essentially, we're going to go over every single element in this row vector and do the multiplication with the corresponding element in this column vector, and eventually add all these multiplication results up, and that's the dot product. And we assign the value into this element in C with the coordinates I and J. So with these 3 levels of loops, we can implement such a matrix multiplication operation in a serial fashion. Now, to look at this solution from another angle, we're showing here the same diagram. We're trying to calculate each of these elements in the matrix C using the dot product of this row vector of A and column vector of B. As we can see from this diagram, and also from the previous implementation in the C code, we can see that the 2 outer for loops, they work independently. So essentially, we can go over every single row and every single column of the resulting matrix C. And it doesn't really matter how we do that. We can go through every single one of rows in a random fashion, or every single column in a random fashion. It doesn't really matter. And for each of this element in matrix C, we can think about this as a separate work item. The concept of work item has been mentioned earlier when we discussed the OpenCL concepts. And this work item can be created for each output element of the matrix. Essentially, in the hardware implementation, no matter you use FPGA or GPUs, the processing elements will perform the computation to calculate this resulting element in C. So what we can do is, for this matrix multiplication, because these work items can be created independently from the other ones, we can map these two outer for loops to the two-dimensional range work items. So if you think about this is the resulting matrix, and each of this element is one of the two-dimensional, so this is kind of the x dimension and y dimension. Each element is one of the two-dimensional range work items. So with this understanding, now we can implement such matrix multiplication in OpenCL kernel. Keep in mind that for a single kernel, we are only focusing on the work that has to be done on a single work item. So if we go back to the previous slide, we know that the single work item is to calculate this element I of j at this element C at coordinates I and j, and the way we'll calculate is by doing the dot product of this row matrix. The way to calculate it is to use this row vector and column vector and to do the dot product. So let's look at this kernel implementation. The kernel is named as simple multiply. Keep in mind we have to add this underscore kernel, this reserved keyword, to indicate that this is a kernel function. And the return of kernel function is void. There's really no return value from the kernel function itself. With that said, it doesn't mean we cannot return results through vectors, through buffers. This is really what we are doing here. This first argument for this kernel function is the pointer to output matrix C. This underscore global is to say that this buffer or this resulting matrix is going to be stored in a global memory. And the type of this buffer is going to be float. So every single element in this buffer is a floating point number. And then we have the next four arguments are the width and height of the two input matrices. So we have width of A, height of A, and width of B and height of B. The last two arguments of this kernel function are the pointers to the input arrays or input matrices. And both of them, input A and input B, are pointers to global memory, and they are of float type. So this is the definition of the kernel function name and the list of arguments that this kernel function requires. And when you instantiate this kernel or call this kernel from the main function, you have to supply all these arguments in the proper order. The body of this kernel function is as follows. As you can see that we're going to get the coordinates of this element, and which is the work item that we're focusing on right now. And because we're using two-dimensional computing domain, as we showed in the previous slide, so that's why we use global ID 1, global ID 0 to get the position information in this x dimension and y dimension. It doesn't really matter which coordinate directions you use, but we're going to have to use these two dimensionals. But we're going to have to use these two dimensions to get the index from these global IDs. And then we're going to initialize the this variable sum to be a 0 to get ready for accumulation. Following that, we have this simple for loop, and we have the loop variable I iterates from 0 to up to the width of A, and then we're gonna do this dot product operation, which essentially do the multiply on this element of row vector from A and a column vector from B. So this for loop is essentially the innermost loop in the original C implementation. Now we have to be very careful in a way that we calculate the indices for this input A array and also input B. So this input A is in fact the row vector, and then this input B is in fact the column vector. Now because we are talking about row vector in the input A, so we will have to use the width of A times the row, the indices that we got from this dimension 1. We use it at the row index, and plus this I. So this is how we store the two-dimensional input matrix into a single dimension array, because in the physical memory everything is linear. So we have to use this row multiplied with width of A plus this width A, which essentially iterates through the width of A. Similarly, we have to calculate the index of this column vector B. And because it's column vector, so we're going to use this I times the width of B, because that's how many elements in a column. And then we add that with this column number that we get from the global index. So I think what's important here is you need to understand why and how we're going to use the row numbers and column numbers to calculate the right index to find the right element in this row vector in A and column vector in B, in order for us to perform the dot product operation. Once this for loop is completed and we get the dot product result in sum, and we're going to assign that into this resulting element in C. Again, we have to be careful how we use the row number and column index number to calculate the indices in the linear fashion, because again we're storing this matrix C in the physical memory, which it has a linear address space. And the way we calculate is to use the row number times width of B, which essentially is the width of C, and we're going to add that to this column number. So that's the exact location of this resulting element in C. So that's the kernel function. Let me just quickly review this. We have the kernel function name, and we have a list of these kernel arguments, and we have these two statements to obtain the indices in the two dimensions that we're going to use. And then we initialize this sum variable with 0, and then we're going to go through the iterations of these elements in the row vector of A and column vector of B to calculate the dot product. And then we assign the result into the corresponding element in C.